I think this team has already been introduced in the morning session. I'll not waste much of the time. You team can take over now. Thank you.
So good evening, all of you. So my name is Deep Chauhan, and I will be presenting here our work on the external DC power boosting drive for enhancing vehicle speed. So as you can see in the image, this is the hybrid towed gun system. So it has a capability for the scoot and scoop. So as it is required for the rapid fire and displace itself. So this particular things in the muddy and sandy area we require to enhance the speed for this particular drive. So it is like a self-propelled mode. So in the self-propelled mode, the maximum speed was consumed by this the combined effect of the pump and the engine. So which is already at its peak. So we cannot add more power to this particular hydrostatic drive. So what we require some concept so we can enhance the speed for this particular hydrostatic drive. So which without modifying the existing hydraulic infrastructure as well as these concepts would be compact and the on power demand like so so we have introduced the DC boosting drive so we can externally supply this hydraulic power to the main drive of this hydrostatic drive. So as you can see in the image, that is the circuit for the booster pump. So it is connected with the, it is like a fixed displacement gear pumps with connected with the DC motor, which inject the flow to the main drive in the high pressure side. So basically flow direction is controlled by the DCVs. As you can see, there is a 4 DCVs. So based on the joystick operation, these DCVs are operated and the flow is going into the higher pressure side of the main drive. So this is the this particular concept is like on demand. So whenever the operators want to operate this boosting power, it will directly switch it, and it can operate. It is like without we are changing the existing hydraulic infrastructure. We are adding the power to the main drive. So as you can see in the circuit, the is the hydraulic booster circuit. So it is like a pump specification are the it is 11 cc revolution per pump, 11 cc per revolution. So each pump each pump flow is going to the main drive, which is like a right transmission and the front transmission. So so each pump flow that going to the each of the main drive like one flow is going to the right transmission and second flow is going to the left transmission. So both twin pump is utilized for this particular operation. So as you can see, the total booster flow is like a 44 lpm at 2000 rpm. So it is adding 22 lpm per main drive per loop. So which is increasing in the motor wheel motor speed by 5.7 rpm, which is approximately 1.5 kilometer per hour of the vehicle speed. So for the control and logic part, so we require to synchronize this particular boosting drive with the main drive. So actually, when the operator operates this particular boosting drive, so it should be synchronized with the joystick of the main drive. So whenever we are moving forward, then there is a two forward DCV will be on, and which will supply the flow to the higher side of this particular main drive. And when we are in a reverse mode, when we are moving our vehicle backward, so another DCV will be operated, and it will supply the pressure on the other side, which is higher side of this main drive. So as you can see here, so in the this is the booster pump circuit, and when we want to operate the forward, so this first DC will be this second DCV will be operated, and this fourth DC will be operated. So it will move this vehicle forward when and it will edit the 22 flow of for both the main drive. So to validate our concept, we also done the simulation for this in a MCM. So as in a previous circuit, as you have seen, as you have seen that booster pump is supplying 22 LPM and injecting 22 LPM to the main drive. So we are introducing additional LPM to the main drive circuit, which will directly lead to the additional pressure rise for this circuit. So for this particular study, we have done the simulation. So our main purpose of this simulation is like we want to check that additional injected flow should be diverted to the flushing valve, and for the flushing. It should not raise the pressure in the main drive circuit. So all additional flow should be go out from the flushing valve without disturbing the main drive pressure. So as you can see, we have simulated two conditions. First is like without booster pump, and second is like with booster pump. So in this left side of image, as you can see, without booster pump, we are getting around 13.5 liter per minute. Uh, when our when charge relief setting is 20 bar. So, and with booster pump, we are getting around 29.5 LPM from the flushing valve, and the 5.5 LPM from the charge relief valve of the main drive, which is directly actuating the charge relief during this additional flow, which is not recommend for our concept. So what we have done, we have increased the charge pressure relief setting to the 24 bar. So as you can see in the right side of image, during the booster pump off, it is same as the 13.5 LPM is going to the flushing valve. When booster pump is on, so additional whatever the 22 LPM we are supplying, that is total diverted to the flushing valve. There is no actuation of the charge relief setting. So that we are confirming from this simulation. For the add-on, we have also test for the emergency operation, as it is not connected with the engine. So during the engine fails, when our main pump is not in the functional mode, so during that we have tested this DC boosting pump. So with this we can say like for 22 LPM, it is giving the speed of 0.6 radian per second, which is vehicle speed of 1.5 kilometer per hour, which is shows the basically it is shows that that without main pump we can operate this vehicle motor with this DC boosting only. So that is the one benefit for us, which is in an emergency mode. In an emergency mode, we can operate this particular vehicle. So after this, we have this testing and validation plan. So as you can see here, this all the testing parameter for the DC motor. We have required to test it is torque and current run and under different load. So as it is supplying 44 LPM, so the power it delivers is like 40 kilowatt, so at 200 RPM. And the for this particular it is current limit is like 194 ampere. So for the gear pump verification, so it should be supply 22 lpm, what we have assumed, so at the 151 bar. So and for the battery test, there is a discharge profile we want to measure. So it operation is like in a 15 minute. So whenever the user want to operate, it will on. The battery should sustain for the 15 minute at 80% of DOD. So for the loop stability test, so observe the system pressure, like in a main drive when we are adding this particular boosting flow. So our pressure should not rise more than 5% at less than 10 degree. So and for the flushing valve testing, we are also want to test the flushing valve, because we are assuming that all flow will divert it to the flushing valve. So we also will test the flushing valve performance for this particular operation. And the as I mentioned the control part. So for the synchronization, we want to also test like when we are operating the main drive and we are operating also the boosting drive, we the synchronization what we have planned, it should be work. So that test we are also uh, planning to do. So and the speed and enhancement trial, so it is like a field trial when what our main purpose is, like during this boosting, our vehicle speed should increase around 1.5 to 2 kilometer. So that is the range for this in a self-propelled mode when we are operating boosting as well as the main drive. And the last is like a system safety and fault detection. So we are here like measuring the overcurrent when we are operating this boosting pump. So we are also measuring the overcurrent as well as the overpressure at the boosting level. So there should be the interlock for us. So, so benefit of this particular boosting is like, as I mentioned, it is enhancing the vehicle mobility. Like it is increasing the 1.5 kilometer per hour. So and it is no drive, and second is like a no driver drivetrain redesign. Like we are not modifying any main drive system. We are not changing any infrastructure, hydraulic infrastructure in the particular system. And like it is compact and modular, we can attach and detach easily. It is like mounted on the chassis of the vehicle, so we can attach and detach. So energy on demand, whenever the crew member wants to operate this, he can easily operate. And in the last, there is a emergency mobility support. As I mentioned, during the main pump off, it can also operate the vehicle by giving the boosting flow. And challenges like limited boost duration. Like I have mentioned, it is can operate only operate in the 15 minutes. So that is the one. And thermal management, due to the additional flow, we are challenges for the thermal management, thermal increase in the thermal uh, temperature rise. So, and the third part is like a control synchronization. We have to sync with our original vehicle and we have to test it. That is the challenges for us. So, by introducing this, we are also changing the main in the main drive hydraulic circuits. So it will add the system complexity. Like we have to change in the main drive to attach this particular boosting drive. So, and then third is like it is not attached to the engine. It is like totally managed by the additional DC motor. So, dependency on the electrical subsystem. So, this particular things, as I mentioned, it is applicable for our defense purpose. Like it is like we are in the muddy stage, like in a sandy stage where when we want to increase our vehicle speed. So that time we can use this particular boosting, and we can increase for that particular scoot and scoop operation. So and the construction infrastructure, it is also been used for the emergency operation where we want more power required during this operation, like compactors, pavers, and loaders to enhance the mobility. And in agriculture machinery, we can also same we can use for the use this boosting like for the additional power, like when we are required the high traction effort and the during the transition speed, all those things. Thank you.
Thank you, Gaurav. It was a nice presentation. I have one question. It can be used in a regular vehicle as a standalone? Because this is a design which you are going to introduce to increase. For
Yes.
any of the vehicle which is currently running, can we use this circuit as a stand and as an attachment?
Yeah, we can use, but it is like a short duration.
But it is only giving 1.5 to 2 kilometers.
Yes, but in a vehicle, like we are using this in a defense purpose. So it is increasing 1.5 is like very uh, useful for us.
Can it be used in heavy vehicles? Here you are only showing three particular applications. Can it be used in heavy vehicles?
Yes, like when we are require additional power, like in a like we have a high torque demand, and we also want the speed increase, then we can use these particular things.
Okay, thank you.
Yeah.
Yeah, yeah, very interesting presentation. I did not understand one of the two scenarios that you played out. One is for 20 bar and another is for 24 bar. Can
Okay.
you just go back to that and just explain?
This one.
Yeah, this one, please. Why did you need that 24 bar?
Actually, this particular in the left side image, we uh, don't want to actuate our charge relief setting, charge relief pressure setting.
Okay.
Like during this boosting, that all flows would go and diverted to the flush valve only.
Okay.
But in the simulation, what we have observed that during this boosting, our charge relief valve is also actuating. So charge relief valve, like in a main circuit, if you see this particular,
So what was your initial assumption for the charge relief valve setting of 20 bar?
like a 20 bar we have set it.
How did you come to that figure of
Like
20 bar in the first place?
actually in the main circuit, this is supplying 42 lpm. So it is has some power to supply in the circuit, and the 10% should be move out from the flushing valve. So that after that 10% will move out this flushing valve, we require to again introduce some flow to the circuit. So we have chosen this 20 bar as per our requirement.
Okay, but so basically you used a rule of thumb to come to that 20 bar.
Yes, like what
It's-
power we need in the main drive during
Okay.
the operation. That particular things we have selected as
So practically you saw 20 bar is
20 bar is
not sufficient for you to ensure that the entire overflow is flushed out without affecting the
actually when
other
we are
circuit.
introducing this boosting particularly, and we are seeing that our charge relief are also actuating.
It's also actuating.
So we don't want to actuate this particular valve during the boosting.
So now with this particular observation, are you now able to confidently say that if you have a similar circuit, what should be the setting for the charge relief valve?
Like 24 bar.
24 bar is
Sir,
your observation, but if
I
you
also have a point here.
Yeah, sure, please.
So, one is that we have a proportional solenoid valve on the pump, so that operation also requires a pressure. So, we are getting commercial off-the-shelf pump,
Okay.
So the charge pump and this relief setting is inbuilt with the pump. Okay.
Okay. Okay.
So you need that much pressure to operate the spools and control the displacement of the pump.
Okay.
Here we have a joystick which the driver operates based on the terrain and then proportionally gives the flow, and accordingly the vehicle gun speed is decided. Now their concern is they are pumping in excess flow from an external circuit. Now if I go and open that relief valve on the other side, motors, I will not call it return line being a closed loop, the low pressure side I would say.
Okay.
So that would go and relieve the oil through the charge pump.
Correct.
That relief valve capacity would be low because it is designed for the pump. So the objective of the simulation is how do I take out that flow once the motor has operated.
Okay.
Okay, so for us this application is mainly based on as he used that word shoot and scoot. Immediately, once you fire you give away your location, so you have to immediately leave. At that time that inrush flow is what we are looking at here. For other applications, what is more important is what is the resistance that plays a role, because I am pumping in something, there has to be pressure difference for this flow to go there.
Okay.
Else it will not work. For here, there's being on a static condition, quickly move from that location and at least go to a certain distance. After that it is stored. So I would say like hardly 300, 400 meters, this gun has to go quickly and leave that location.
Okay.
So that beyond that it moves away.
Okay.
So this is what the whole
So basically you want to
application
use
is.
the same arrangement for multiple scenarios like shoot and scoot and other
Yes,
applications
yes,
also. So
yes,
this is the
yes,
golden
yes,
mean that
yes.
you have achieved.
But challenge here is negotiating a slope. That would be a challenge because at that time the closed loop pressure itself would be more, so pumping in something from the outside would be a challenge. That flow may not go, or your external circuit should be at a higher pressure so that there is a pressure difference created and the flow enters this loop.
Okay.
So those things need to be studied. For now, we are just looking at using it to come out of action and quickly move from that spot.
Okay.
That is the application point of view where this is going to be used.
Like in a slopey area, we require about 400 bar something to actuate this main drive. So our DC boosting should also be operated at 400 bar.
Right.
So that
Right.
for challenging for us. So
Okay. Thank you. Thank you.
I think we will leave other questions for after, for offline, right? Can I request Mr. Sahil Khurana from Hyundai Construction Equipment to please give the memento?